We'll begin this problem by finding the expectation value of the ground state of the simple harmonic oscillator. And as you may recall, it is the integral across all space of the wave function, the complex conjugate of the wave function, and then times the operator, the position operator acting on the wave function itself. Now, if we look over here to the left, we found these in another problem, but we can see that the ground state of the wave function of the simple harmonic oscillator is an even function. So since that's an even function, and then this is an even function since the simple harmonic oscillator doesn't contain any complex terms right now, and this is an odd function, this whole thing is going to be an odd function here that we integrate under. And so that means that the integral is going to be 0. And the same thing goes for the expectation value of the first excited state. For the rest of the problem, I'm just going to do this indefinite integral and just not do the limits. It should be understood for the rest of the problem. So when we do this for the first excited state of the wave function, as you can see over here, this is an odd function, this is an odd function, and this is an odd function. So all three of those odd functions make an odd functions, and whenever you do an integral of those over symmetric boundaries, that ends up being 0. So the first values that we found are going to be fairly trivial. That is not the case as we move forward, not necessarily for the momentum expectation value, but for the momentum squared and the position squared. Anyways, so whenever we do the momentum expectation value for the first ground state, one way that we can think of this is just the operator acting on the momentum operator acting on the expectation value of the position. And since this is actually 0, which we found out over here, that means that the momentum value, the expectation of the momentum for the ground state is going to be 0. And also, as you can maybe guess, that this is going to be equal to 0 too, because this will just be the expectation value of the first the first excited state, and that's just a 0 for the position value. Now, this is where things start getting interesting whenever we get into the expectation value of the position squared. So whenever we think about this, let's go ahead and write it out a little bit more explicitly. So in the problem, it gave us a hint to write these out so in different terms, and we will substitute alpha for this term right here. And then I also suggest to use zeta for this term right here. However, I don't really like that much. I think the integrals are a little bit easier to solve if we make a different substitution. So it said that, actually. But I think it's actually easier if we do it like this. So I'll go forward with the problem using rho as that value here. So what this ends up being is so when we do the ground state of the simple harmonic oscillator, it'll end up being alpha times this exponential, rho squared over 2 x squared, times the the position expectation, or the position operator, times this. Nothing too exciting with this one. It ends up being that the alpha ends up moving through the integral sign since it's a constant. Sorry, I almost forgot that one right there. This ends up being rho squared x squared dx. Now this integral is one of those integrals that you'll just end up working a lot with and potentially end up memorizing. Or what you can do is solve it analytically by hand. I wouldn't really suggest it. I would suggest actually using an integral table or Wolfram alpha, one of those two sources. Now we'll go ahead and apply these values. And actually, before I do this, I'm just going to go ahead and copy these down to the next page for reference. So alpha squared will end up being the m omega pi h bar, and that's just going to be the square root of all that. And then, let's see here, square root of pi. I'll just go ahead and open up all these values, resubstitute them in. Now we'll go ahead and start canceling out like terms, start doing the algebra. And as you can see, we end up getting something very familiar, something that makes intuitive sense in terms of the answer here, right? We would expect you can go in and check the units, and this will end up being in units of distance here. Units of distance squared, since it's the expectation value of the position squared. So that was for the ground state. Now we'll go ahead and going down to the first excited state. So this will end up being the first excited state will end up being, let's see here. Go ahead and so we'll just go ahead and move the constants out front. You can go ahead and just sandwich the x squared in between the two values for the first excited state, and it just ends up being relatively easy to do. In the textbook, it tells you exactly what the ground states, or what the first excited state equals, something exponential. But you could end up just skipping to that part since it's just moving integrals through. So we'll go ahead and pull out the whole squared. Again, this is one of those integrals that is best used in a calculator or using an integral table. After a while, you might be able to just recognize it and kind of understand the heuristics of it. So we'll go ahead and cancel out our terms. Let's see here, 3/2, move that constant out in front, pi squared, or square root of pi, this would be rho to -5. Actually, since we have, let's see here, because we're expanding out these terms here. Now, we're going to go ahead and expand, this is maybe the tricky part, we're going to go ahead and expand this out to its constituent values in terms of rho. It'll make sense in a second. So now this ends up being, let's see here. We'll go ahead and we'll just go ahead and, unsubstitute the values for alpha squared. So that actually is m omega pi h bar. Then times our rho squared, which is just m omega over h bar. We have our square root of pi here. And then finally, square root of m omega h bar to the -5th. And so we can do one more kind of, I don't want to necessarily say trick. Let's go ahead and actually just kill off this pi right here. So that'll be 3/2 m omega h bar. The reason why will be clear in a second while we got rid of that h bar. So now we can actually expand, we can go ahead and expand this into m omega, right? Because it's to the -5th, so we can pull out a square or a squared. And then all that's left is, it's not very good looking, square root. This is actually inverse, so we're just, again, just expanding this out to this value here. Now we can just really start knocking out terms here. This one here, this one here. These go away, these won't go away, and this takes care of one of the squares here. And all that's left is 3/2 h bar over m omega. The same units that we would have gotten here, but just different values for the constant out in front. Okay, we're almost there, everybody. We'll go ahead and move down to the rho squareds. Sorry, the p squareds, momentum squareds. So this is actually going to be for the ground state. little tricky. So we have our integral. Again, like I said, it's over all space. We'll go ahead and substitute in. I'll be really explicit with this one because this one can get kind of tricky. So this is just the ground state of the simple harmonic oscillator using the constants. Now, the constants suggested by the textbook. So now we have to apply the momentum operator twice. It's not as easy as before on the other parts of the problem where we just kind of threw it in there and then just used algebra to move things outside the front. Now we actually have to perform an operation within the integral sign here. So we'll go ahead and throw that in there. And then this will be in here because there's no complex terms inside the simple ground state of the simple harmonic oscillator, dx. And again, I'm going to go ahead and forego the integral sign here, but we can start pulling, or not forego the integral sign, but forego the limits. We can go ahead and pull out some of these constants here. So we'll go ahead and pull out the 1 over I squared, which will just be in the negative sign here. We have our alpha, and we have our h bar. There is our integral, and then we have our exponential left here, x squared. Now we'll perform the first derivative on it. We're just going to go ahead and apply one of these derivatives to this here. So it'll be 1 over rho squared over 2. And then the derivative of x squared, which is just 2x. And then e to the negative rho squared over 2 times x squared. So that's one integral down. We'll go ahead and just do some bookkeeping, cancel out the like terms. I'm going to go ahead and, for this next start, pull this negative sign out in front. So now we have a positive alpha squared. We still have our h bar. And then we have integral. We still have this. I'm just going to go ahead and just bump this down since we're concentrating on derivatives. And now we're going to apply this derivative, first derivative, to the derivative that we already performed. So now we're going to have to do some product rule since this is both have x on it. So we'll go ahead and do x times the derivative inside again. Okay. So it's x times the derivative of what's inside plus just the derivative of x, which is 1, of course, and bracket dx. Okay. Not too bad yet. We have a rho squared here, so we'll go ahead and let's see here, do a rho squared. So we'll go ahead and pull one of those rho squareds out because this actually had a, oops, sorry, I should have pulled the rho squared out right here since that's a constant. So let me go ahead and make room for that. Almost forgot about that term. Can't pull it out here because of this. So now we're just going to go ahead and simplify everything that's out front here, or inside the integral sign. So do positive rho squared, alpha squared, h bar squared, lots of constants. Now on the inside, we're going to go ahead and factor out rho squared, x squared, because there's an exponential here and it times, there's an exponential here and it times the exponentials in here. And then you can pull the exponential out so that you're just going to have rho squared instead of rho squared over 2. And then just 1 minus x squared rho squared dx. Over infinity and negative infinity and all that. So again, this is one of those integrals where you're going to want to use a table. And this will be equal to, I'm just going to go ahead and put in parentheses, square root of pi over rho squared, and then times 1 over 2. Let's go ahead and expand out all of our substitutions we made, such as rho squared. Rho squared is actually just m omega over h bar. Alpha squared, well, it's going to be under square root, so I'm not going to do that. Alpha squared is a square root of m omega over pi times h bar. Of course, we have our h bar squared here. We have our pi. Let's do Oh yeah, we have our rho squared. Square root of 1 over rho squared. So we'll just go ahead and write it like this. Times 1/2. Let's start knocking out like terms like this one, these two here, this pi right here. And then let's see here. We had, there we go. Let me make sure I got everything. Okay, oh yeah, sorry. These two actually didn't. These are the ones that ended up canceling out these and this. We have a h bar here, which kills off one of those h bars. Again, like I said, a lot of bookkeeping in here. I'm gonna go ahead and move that 1/2 out in front. So you have 1/2 omega h bar left over. Okay. Our last expectation value that we're going to solve for. Again, they're pretty tricky. So for this one, I'll go ahead and write it out explicitly. I'll just write the limits once. So the first excited state of the simple harmonic oscillator, in terms of all of our constants that we had, is equal to this, FL2 m omega. And again, this is in the textbook if you need further clarification on this, except I do rho instead of zeta. Personally, I find it a little bit easier to work with the constants out in front, just because of, like how I said, the calculators and all that stuff, and the integral tables. I'll use shams or something like that to calculate. I'm just going to put ... some of these integrals. I'm running out of space here. I'll just go ahead and move that integral or the equal sign out in front. So first things first, let's pull out some constants. Like these will multiply by each other and go out in front. Alphas are a constant, so I'll be alpha squared. This will be a 4 since there's two 2's, and m omega and omega there. So let's go ahead and write those out. So it'll be 1 over 2 h bar m omega alpha squared m squared omega squared. I think that's it. Oh, nope. There's a 4 in there, of course. So there's the 4. Before we actually start throwing things under the integral sign, let's start canceling out for some bookkeeping. So this 2 goes away. This 4 turns into a 2. H bar. Nope. H bar still stays down in there, I believe. Actually, you know what I forgot? Let me move this out in front. These guys. So there's a -1 in there as well. Whoops. There's a -1 and h bar squared. So that h bar here kills off one of these h bars. M kills off one of these. This omega kills off one of these omegas. I think our bookkeeping is done. We can move into the integral sign. All that's is left over. And I'm just going to go ahead and put this once, and then I'll just drop it down like I did before for terms of the bookkeeping. Let's go ahead and apply one of the derivatives in here to this chunk right here, which is really just this xe to the exponential here. So we'll have an e. So we'll just do the derivative of, you know what, I'll just go write it explicitly. Derivative of x, this is again like a product rule. -x, because this is a negative value that comes down, 2x, e to the negative exponential. I'll just put ... here. Again, bookkeeping before we go on, it's always good to tidy up. Things will start looking more condensed. We'll go ahead and do an alpha squared m omega h bar with a negative sign out in front. Believe that's it. Oh no, and a 2. Almost got me on that one. I will go ahead and put, just because we're going to be working with a lot of this, just move this here. Compress space a little bit. All right, now we're going to do another derivative of everything that's in here. So we'll concentrate on this term right here, Derivative of that is relatively easy. We've done that before. Negative falls out. Rho squared over 2 times 2x times e to the negative rho squared over 2x squared. All right, now we're going to have to do another product rule. So this will be negative 2x rho squared e to the negative rho squared over 2x squared. And then here's our x squared here, rho. And then rho squared actually, times what's inside here. This is chain rule. It's a negative dot, dot, dot. And parentheses dx. Okay. Let's do some bookkeeping. We'll go ahead and knock those out. Is there anything else? Knock these out. Okay. One thing that we can immediately see is that there is a rho squared x, rho squared x, rho squared, and an x, or here's an x, all common to those. So we'll go ahead and factor those out. And an exponential in terms of all those as well. So let's go ahead and factor that out. We have a negative sign out front. I like to write it in bold so I don't forget. Okay. I don't believe there's any constants. Let me just do a quick check. Yeah, it doesn't look like there's any constants that I can pull out. This is no longer a rho squared over 2 anymore because we pull out one of the exponentials from this parentheses. And then times the quantity of, since we pulled out the rho squared x and exponential out of these, all that's left over for this whole term is just negative 1 minus, that's basically everything from this one. So that's just 2 that's left over here. And everything that's left over from this term is just an x squared, positive x squared, rho squared, dx. All right, let's go ahead and slide this up a little bit. I'm going to go ahead and throw this negative sign in there. Change the terms around a little bit, but I'm just going to make a positive. Oh boy. Excuse me. I don't know what happened. Positive m omega h bar 2. All right. So let's just go ahead and just do one more simplification. Doesn't hurt to be more explicit with these tricky things. So just to really show that I threw that negative sign in here. That's what we got. So this is the integral that we're going to be working with here, actually. Well, you know what? Actually, this is a constant, so let's go ahead and throw that out here. There we go, nice and tidy. Now, that's our integral that we're going to be working with. And like I said, it's always good to do these like in a calculator or table. All right, so what this integral ends up being, of course, over from negative infinity to positive infinity. This will be ended up 3/4 over the inverse of what's in the exponential, and like what's over here is they're going to be matching, times the pi over rho squared square root. There we go. All right, let's go ahead and we can just go ahead and knock this out. Just do some bookkeeping. This rho squared goes away. This 2 goes to 1. This 4 goes to 2. And while we're at it, we're going to go ahead and just expand out our little constants that we have here. So alpha squared ends up being m omega over pi h bar square root m omega h bar 3/2. And now we just have a square root of pi and a 1 over rho. Let's go ahead and explicitly write out rho. So it'd be the inverse of h bar. Whoops. That would just be m omega over h bar inverse, square root here. All right, so again, more bookkeeping. These pi's go away. As you can see, this whole portion right here is knocked out by this portion right here. And what we're left is with something dimensionally intuitive and exactly what we're looking for. And that is the momentum squared expectation value for the first excited state.